Start recording. There we go. Okay, so we have, I'll do a bit of housekeeping up front here. We have 3 meetings left, including this one. We have this one, there's one next Thursday. Then the Thursday after that is Thanksgiving break. And the Thursday after that, we're meeting again. And then the Thursday after that is like exams week. So just 3 left. Unfortunately, we did end up having to cancel some of these, or I had to cancel some of them because I had 2 tests like exactly on the day and time that this was supposed to happen. So we didn't get through everything that I planned, but the goal is still, I'm skipping out on some of the other stuff that I had planned because the goal is still to, like, using everything that we've talked about, look at a very difficult problem and design some type of solution, or at least look at a solution that I've designed. So today we're going to finish off data structures from last time. I was sort of rushing near the end, so I just want to like brush over that again. And then there's a couple more things I want to talk about. And then the rest of the time today, I think, will be dedicated to me introducing the problem to you. We're not going to actually get to like solving it yet. But yeah, let's go ahead and get started. So where we left off last time, I believe, so we went through like array, linked list, trees, stat queue. I did go through priority queues. I think I rushed through those a bit, so I'll go over them just briefly again. I think we also talked about hash tables for dictionaries at the end, and I said about everything I need to there. So yeah, let's start with, well, let's not start with priority queues. Let's instead start with tree traversals, because that's something I realized that I sort of just assumed everyone knew last time, which is, you know, not a very good way to teach. So let's say we have some binary tree here. Very simple, it doesn't have to be very big. And we will look at 4 different types of traversals. Traversal meaning ways of touching every element in the tree in some type of order. So I'll avoid writing order for all of these, but this is pre-order, in order, post-order, and level order. So pre-order, and keep in mind that we only have the root. Whenever you have a tree, you only store a reference to the root. That's the only thing that you actually know about. Okay, so pre-order goes through all of these. So, well, actually not all of them, but these 3 right here follow sort of patterns that can be described with 3 letters, L, N, and R. L meaning the left child of a node, N meaning the node itself, and R meaning the right child of a node. Level order is a bit weird, and we'll talk about that at the end. So pre-order is in LR, in order is L in R, and post-order is LR in. So all you have to know here is that L always comes before R, and then the position of in relative to those other 2 tells you which type of traversal. So pre, meaning I look at myself, the current node, before looking at either of my children. In order, meaning I look at my left children, then myself, then my right children. And post order is I do myself last. And these are just sort of useful acronyms because these words, like I have just trouble remembering what those mean. But if I can remember these acronyms, it makes it a lot easier. And also using these, we can now sort of go through our tree and just trace out these traversals. So let's do the pre-order one. So I print out at each node, I go to myself. So I print myself, then I go to my left children, then I go to my right children. And that's a recursive process, obviously. So starting at the root, myself is A, then I go to my left, myself is B, I go to my left, myself is D, no more children. So I return back up to B, and then I go to my right of B, which is E, no more children. So I return up B, B has no more children. So I return up to A, and now we do finally the right child of A, which will be C. So that is the pre-order traversal of this tree. In order means that we go all the way down to like the very bottom left of the tree first, because we just keep on doing the left child first. So we'll end up with D, B, E, A, C, left, L in R, and this is the L in R right there. And then post order is somewhat similar. It's going to be D, E, B, C, A. Okay. So these types of traversals are just good to know, even if you don't necessarily like directly use any of them for particular things. Like, I mean, it depends on how you implement your tree, of course, if you even need more than one of these, but it's just a good exercise to sort of get you thinking about the recursive nature of trees and how you can easily process them, I guess. Level order, though, is not nearly as simple, unfortunately. Level order is where we go through and print all of the nodes on each level from left to right. So a level order traversal. So this one will do the opposite. We'll look at the result and then look at how it's done. So in this case, a level order traversal of the root gives us A, B, C, D, E. And then if there was something here, it's like F, then F would come at the end. Okay. So level order, I think before I even explain how it's implemented, we can look at how it's sort of used, because what's the point of knowing these things if you can't use them? And how we can use it is for priority queues. Priority queue or heap. These are also called heaps. And just as a brief recap of what these are, they're built on top of array trees, generally. So trees that are implemented not as a collection of linked independent nodes, but as an array where each spot in the array represents some node, and whatever value is in that spot is like the data that that node contains. So when we have a heap, it's just an array, and it turns out when we add something to that heap, it's not quite as flexible as adding to a tree. Because if we have a tree, we have a bunch of independent nodes, everything is just connected with pointers. So if we need to, we can just swap around those pointers. But when everything is shoved into an array and the indices need to be maintained because the indices govern the relationship between parent and children, we can't just shift everything around, right? Because that would completely mangle our tree. So let's look at a simple, like a super simple example of this, because I don't want to spend too much time writing everything out. So in memory, this would be like this, very simple. But now let's say that I want to add another thing as like the left child of C. So I have A, B, C, and then I'll add D. We'll need a bigger array here. So we have A, B, C. We have 2 spots for B's children, and then 2 spots for C's children, and the left one comes first, so we would have D there. And what we've done essentially here is a level order insertion, because we added something like at the, because there was no space left on this level, no space left on this level. Well, actually, that's not true. This is a bad example. Let me redo it. I should have added that as the left node, the left child of D. Or sorry, left child, I should have added D as the left child of B. Because now that's a level order insertion. We insert from top to bottom and left to right. So at each step, whenever we want to add something new, we just put it in the leftmost position in the like current bottom layer. So if I were to add another thing, E, that would go there, and then F would go here, and then eventually we would get and drop down to a new level. And this turns out to be a very convenient way to insert things into an array tree, because if you've noticed, all we're doing is just adding to the next slot in the array. That's just how the math works out there. Which is nice because it means we don't have to do any shifting or anything. We don't have to worry about maintaining the structure of our tree because we're not changing the order of anything else. We're just tacking something onto the end and it ends up in the right place. Now, in heaps and priority queues, which are like ordered data structures, there is more processing that happens after you insert, but you always insert at the end. And that is what's called level order insertion. So how does that tie back to our level order traversal? Well, unfortunately, we still don't really have an answer. To get an answer to that question, we have to look at a different type of data structure, one that you have probably heard of and are probably somewhat scared of, which is graphs. So graphs are, I think of them as like more general trees. Graphs are just any sort of collection of nodes like a tree, but they are not ordered as strictly as a tree. You can have, relationships between any that you want, just like this. Those relationships can be one way as well, as in a tree, because a parent can reference its children, but usually the children don't have a pointer back to the parent. It's just that because that's sort of the generally accepted convention, we never actually draw the arrows on the tree, even though they sort of belong there. And yeah, so a graph is just sort of a more general tree. And you can do other things too, like assign sort of values to each of these relationships. Like I could say this is 3 and this is 5, and that can be useful for certain things. But let's sort of actually look at a formal, I guess, list of the types of different graphs. So first up, we have, without even caring about the actual underlying implementation or representation of a graph, we have 2 main types, unweighted and weighted. So unweighted is where edges have no value. An edge is just something connecting 2 nodes. It represents a relationship between those 2 nodes. So they have no value. So it just means that, hey, I can get from here to here, but there's not necessarily anything associated with that. Whereas in a weighted graphs, edges store some type of value that represents cost, I guess is a good way to think of it. And that cost could be different things. It could be actual cost, actual money. It could be distance. That wouldn't be uncommon. Like say I have a graph where each node in the graph is a city, and the weight of the edge between 2 cities is the distance between those cities. And these are useful for different types of problems. I don't want to say that one is more useful than the other, because I don't know that that's true. But in general, today, we're just going to look at unweighted, and everything we talk about generally applies to weighted as well. Okay, so that's sort of one of the main, one component of the main types of graphs. The other one is undirected versus directed. And this is the difference between like an edge between A and B. That's just a flat line, and an edge between A and B that has an arrow. So this one means I can get from A to B and B to A. This one means I can get from A to B, but I can't get from B to A. In a directed graph, you can still have 2-way relationships. You would just draw a second arrow there. And you can mix and match these as well. You can have an undirected weighted graph or a directed unweighted graph. It doesn't matter. But yeah, so weight and direction are properties of the edges of a graph. The nodes themselves, it doesn't matter what they are. They can store any kind of data. The only real difference is in the edges. So I don't want to, yeah, we're not actually going to like look at super in-depth graph algorithms, but some cool ones, like cool things you can do. You may have guessed based on my city example, is you can have like just a graph of nodes with connections between them. And each connection has some distance, let's say. So this is city A, city B, and city C. And let me actually, or maybe not distance, but maybe this represents time. Maybe this is like the amount of time it would take to get from here to here along this specific path. So maybe this path represents a highway, the main highway from city A to city B. So let's say I have some graph like this. Well, if I want to get from city A to city B, it turns out that it's actually faster to go through city C somehow. Like in this stupid example, that just works out. Maybe there's some like really bad wreck or there's road work or something going on that edge. But this is sort of the basis. This is like the underlying data structure of path finding algorithms. And this is a general term. Obviously, it's things that, given a data structure, can tell you whether or not there's a path from A to B. But also, usually they involve some, like the minimization of some quantity. Usually for graphs, that would be cost. So we would say, I want to get from city A to city B if possible, and also find me the way that takes the least amount of time or costs the least amount of money, something like that. A very common one is Dijkstra's algorithm. That's sort of the classic one. I think there's also one called like Bellman-Ford or something. I don't know. They're not particularly like interesting, honestly. I mean, the results of them are cool, but the way you do it is sort of just what you'd expect. You just basically keep some structure representing all the nodes that you visited, and you work through and just sort of go through all the possible edges from place A to place B and work out which ones sum to the least. I mean, that's not to say it's not complicated, but I don't think it's that interesting. So that's pathfinding. There's sort of a similar, but also a bit weird type of algorithm called MST, minimum spanning tree. And these work on weighted graphs as well. So say I have some collection of nodes here. Let me draw the edges for them. Let's say it looks like that, and I'll just assign some values to these. So a minimum spanning tree is the set of edges that such that every vertex, every node in the graph is still connected, but it's the least total cost, the least total edge weight. So in this case, this would go to, I'll still have my 5 vertices here, but I believe it would be, oh, I forgot to assign the weight to that one. I believe it would be something like that, because that's 1, 2, 1, and 3. I think that looks like the cheapest way you can connect everything. And these, I honestly do not know many applications of these. I mean, in general, a sort of cop-out answer is to just say, oh, social media, because, you know, that's sort of the like social media platforms are built on graphs. But I've never used these. I mean, pathfinding obviously is generally useful in many cases, but MSTs I've never used. Some things that I have had to use for graphs and other data structures are Dfs and Bfs. And these are big ones. Like, you should know these. I'm not saying you should already know them. I'm saying if you don't know them, you should learn them. They are very common on interview questions, of course, yada, yada. But also they're just not that complicated and they're very useful. So these refer to depth and breadth first search. So what that means is if I have these specify two different ways of traversing a graph. So we looked at ways that we can traverse a tree. We looked at pre-order, in order, and post-order, level order. I'm about to cycle back to that. We need these for that. So these are ways to traverse a graph. So basically, they operate on the idea that at each node of a graph, there are edges that connect that node to whatever other nodes it's connected to. And the difference in these algorithms is the order that we visit those children, or I don't want to say children, those neighbors. So given a node, Dfs and Bfs will visit each of that node's neighbors in a different order. So, I mean, it's basically that simple. I guess I could walk through an example, but the key point here is that depth first search is sort of built on a stack and breadth first is built on a queue. These are the data structures that we insert our new nodes into. So for DFS, which is a generally written recursively, just because it operates on a stack. And you know, when you have recursion, you have the hardware stack that sort of acts as a stack for you, with all of your recursive method calls being stack frames. Breadth first is a queue, which doesn't really have an underlying hardware thing, so we generally implement that in software. But anyway, so for DFS, at each step, you could first check like if I visited the current node that I've been given. So if I've already visited this one, then I'm not interested in it. I've already seen it, I'll just return. Because this is just a way of visiting every node in a graph once. And the problem with graphs that does not occur in trees, like this is a valid tree, you could say this is the root, but this is not a valid tree, but it is a valid graph. And the key point here is that there's a cycle. This is an infinite loop. If I start here, I can end up here, I can end up there, I can end up there again, and you just keep going. So we store some external list of which ones we've already touched so that we don't get stuck in an infinite loop. And then for DFS, all we do is for each child of the current node, we just call BFS on that child. So I think of this as like a greedy algorithm, and you'll hear that term a lot, especially if you look into pathfinding and MSDs and stuff. I think of this as a greedy algorithm because it basically says, as I'm going through a list of things, when I find a new node I can go to, I just go to it immediately. I don't care. Like, oh, you have a child, I'll go there. Which that's the depth first idea, is that for a given node, we don't visit all of its neighbors from left to right. We visit one of its neighbors and then all of that neighbor's neighbors and all of that neighbor's neighbors, all that stuff. Now, this is very clean to write and it's a very elegant solution to many problems because of that sort of underlying hardware stack that I mentioned. Breadth first is, I mean, like algorithmically just as simple, but it's not as clean to implement because we have to keep track of the queue ourselves. But there is somewhat of a benefit because we can just do it iteratively, which can save time over recursion. Okay, so let's say we have a queue, and in this queue, we will put just like our starting node. Just choose some node from our graph arbitrarily, and that's where we start. And then all we do is we loop on this queue And while there are still nodes in the queue, we will say, okay, my current node is equal to queue.remove. Remember that this removes from the front of the queue. And then for each of the current node's children, I will add that child to my queue. And then, I will mark the current one as visited, of course. And I forgot to do that up here, I suppose, as well. So we check if we visited, then we return. And then immediately after that, we say that, yes, we have now visited the current node. And same thing, I also need that. No, well, same thing, sort of. I need to do if we visited the current node already, then we just skip. We just continue, go to the next loop iteration. So this one, in DFS, depth first, we go through our children, we go to each child as soon as we see it. In breadth first, it's sort of the opposite. We store all of the children, so we know they're there, but we go through them in the opposite order. And the effect that this has, if I can draw a quick little example here, I will just do it like this. So a DFS traversal of this graph here, starting at A, would say, okay, I've been given A, then I'll go to C, and then C has a child, so I'll go to D. And then I'll come back to A and go to B. The breadth first one, though, will say, okay, I have A has two children, B and C. I'll insert those into the queue, and then I'll process them in that order. So say again, I choose to go to C first, just for whatever reason that's what it's for. Okay, well, C has a child, which is D, so I'll insert that into the queue. So I've processed C now, but the next iteration is B. Maybe I should write the queue over here. So that should be uppercase. So we have A, and then when we visit A, we say, okay, it has children B and C, and we're done. So we remove A from the queue. We go to B, we say, okay, I've seen that, no children, nothing to add, we remove that. Then we go to C. Actually, I did that in the wrong order. That should be A, C, B. Okay, so we go to A has C and B. C has a child D, which we add to the end of the queue, so that the next iteration then is still B, and then at the end we get to D. And in this case, because it's such a tiny example, the difference is only one letter there. These two are just swapped. But you can see, you can think of it as BFS looks at A and it goes through all of A's children. Huh? The same level. Exactly. It's almost as if it is a level order traversal. Huh. Okay. So let's tie all of this back together to what I was talking about initially with trees. Can I scroll down? Okay, finally, we're looking at level order traversal. Awesome. So in a tree, this is not a graph anymore, but a tree. I will start at the root and just go through it with a BFS, a breadth first search. So I have my queue here, and then I'll have the output right here. So the queue obviously starts with the root. So that's the first thing that's output. And we say, okay, A has B and C. We're done with A. We go to B, that has D and E. We're done with B, we print it out. We go to C, C has no children. We go to D, D has no children. We go to E, E has no children. And what do you know? We have a level order traversal. So BFS, a breadth first search, is, as far as I know, necessary for level order traversal on your typical node-based tree. But for an array tree, such as those used to implement priority queues or heaps, if this were instead an array tree, what that would actually look like in memory is this. Because things are inserted in level order, they are therefore stored in level order. So all we need to do is just print the array out in the regular order, and there you go. You don't need a queue, you don't need any sort of fancy iteration methods. You just for int I equals 0, I is less than r dot length, print I. There you go. Okay. So I think that's all I wanted to talk about with traversals. Now that we know all of that stuff about trees, and assuming that you remember what I talked about with hash maps and stuff, or hash tables last time, let's look at our final two data structures. They are the set and the map. And the set is sort of used to create the map, I guess. So these come in two flavors, tree and hash. That's what Java calls them, tree set, hash set. C++ just calls a tree set a set, and a hash set an unordered set. In Python and stuff, I'm not sure if there's like a tree set, but dictionaries are just hash sets. They do have ordinary set. Yeah, there's probably some, but I'm thinking I don't think they have a built-in tree set. Yeah, but that's a data type. It's not, because dictionaries are like, they have special syntax. Anyways, yeah, these exist in every language in some form. And I think the fact that tree sets exist is actually kind of interesting, because what a set is mathematically is just some collection of data in no real order. The only condition is that there are no duplicates. That's why sets are useful. If I take this set and I try to add A to it, it'll say, oh, I already have A. So it just won't add it. It won't do anything. But a set implemented as a tree is inherently ordered, because a tree is sort of provides a hierarchical ordering of things. That's another thing, just very quickly, that I want to touch on, if I can go back to graphs for like 5 seconds, is I think of trees as providing a hierarchical order. I think of graphs as providing a spatial order, a relationship based on space or time or whatever your cost function is. It just, like, trees are like, this thing is the parent of this thing. Graphs are like, this thing is connected to this thing. Okay. But yeah, there are tree sets and then hash sets, which make more sense because those are just naturally unordered, because of the way that hash tables work, which we talked about last time. But yeah, like, basically all you need to know here is that sets are just collections that allow no duplicates. That's the main thing. Trees are ordered, hash sets are unordered. And you might be thinking, well, if I have a set and the main property of the set is that I want to have no duplicates, then basically, like, I can just use that to check if, like, if I'm in something where I'm visiting a bunch of nodes or something, I can put each node that, well, actually, I don't know why I'm giving this as a like vague example. This is exactly what you could do for like a DFS or a BFS. I mean, depending on how your graph is actually structured, there may be better ways to do it. But say your graph is just a collection of node pointers, then you could put each node pointer that you visited in a set, and then if you try to visit that node again, you check if it's in the set, and if it is, then it means you've already visited it. And so in that case, order doesn't matter at all, because you're just using it as a thing that's like, hey, have I seen this before? You don't need to know what order you saw things in or anything. But as we'll see in a minute, and generally that is true. Unordered sets, hash sets are used far more often than tree sets in my experience. But there are particular cases where having ordered sets is helpful and actually necessary. Okay, so now let's look at maps. So just like sets, there are tree maps and hash maps, or you could think of them as ordered and unordered. And maps are, I think, other than like arrays and maybe trees, maps are the most useful data structure out there. They provide a way of associating two sets of data. They store, so they have two types, a key type and a value type, and they store pairs of elements of those types. So if I have a map that stores, strings to ints, I could insert a pair where the key is a string and the value is an int. And then if I want to see, hey, does my map have this particular string as a key? And it does, then I can just give it that key and it'll give me back the integer value associated with that. Okay, and the same question applies here, which is, well, why would you ever use an ordered map? Not in the sense that like, not quite the same way as with sets, because with sets, it's just like a mathematical idea of a set is just inherently unordered. It doesn't matter. But when you get into maps, it's like, okay, that could make sense that there would be an ordered one. But then you also start, you have to consider time complexity. If stuff is a tree, basically everything is log n. But if stuff is a hash table, everything is about order one. So like, why would you ever use a tree, right? It's just slower. And this is where we get into the ordering of things actually mattering. So this sort of leads us into the problem that we're going to look at. I won't have enough time actually today to cover it, which is fine. I talked a bit more about graphs than I was planning to. But I'll sort of give you a little teaser of it, I guess. So say I have a system that its job is to track the, well, that's not a good way to draw it. I'll draw it properly. Its job is to track the position of a bunch of objects. And in particular, tell me if any of those objects are intersecting each other. And if they are, it tells them to resolve the intersection. Now, in this case, where I just have this sort of arbitrarily laid out boxes, that I don't think that would cause any problems. But if you have a case where say I have a wall of boxes that are all completely flat, as illustrated by my perfectly straight line there, and I have another box that is intersecting two of them. So in this case, and let's say I also have like a perpendicular wall here. That is same thing, just a straight line of independent boxes. So what happens here is, assuming the rest of my system works correctly, it's tracking all these boxes and it says, hey, my box A here is intersecting boxes B and C. Resolve it. Okay, so let's say we just arbitrarily choose to resolve B first. Then what would happen is A would just sort of get scooted back. If I can erase here, A would just get scooted back a bit so that it is no longer intersecting B. And in this particular case, that also resolves the collision with C. Okay, so the way this could be implemented is, say I have a function, my function that checks for collisions. It goes through all of the objects that it's tracking, every pair of objects that it's tracking. So like for box A, and then within that for box B. And then like if A is equal to B, if we're checking something against itself, we don't want to do that, so we'll just skip it. But otherwise, if A is intersecting B, then we will sort of add a collision. So we will say, I don't know, collision.add A and B. There's a collision between A and B. And then once we have found all these collisions, at the very end, we will go through all of them. So for each collision C, we will just attempt to resolve it. I'll write that as actual code. Let's just say there's a method called c.resolve. Okay. Now, in this example here, though, where I had two intersections, so I had an intersection between A and B and between A and C. So my C might look like A and B, and not B and C, A and C. And then I resolve B first, and that pushes A out. So resolved that one. But then I also just unconditionally resolve C. And there's no check to see if A is still intersecting C. So what'll happen then is A just gets pushed back even further from the wall, when really it shouldn't, because these two are exactly the same distance from A. A is intersecting them the same amount. And so resolving one of those collisions happens to resolve both. So a very easy solution to that is just checking, like if collision.A still intersects collision.B, and if it does, then we resolve. So that solves that simple case of like overdoing the collision resolution and ending up with false results. And it's important to note there, like this seems like just a case where it's like, oh, that would be extra work. We don't want to do extra work. Like it might sound like I'm saying, well, B already resolved the collision. So resolving the collision between A and C would just be an extra step that does nothing. But that's not true. It's actually harmful beyond just like wasting time. It's not just wasting time. It will give you incorrect results. Because resolving the collision between A and B correctly pushes A back out from the wall. But then if I then resolve the collision between A and C, then I push A back from the wall even more. And so A can never actually touch the wall, which is probably the behavior that you intended. So it's not just like an efficiency note. This is the correctness note. This step is required for this algorithm to actually work. Okay. So that's just a very simple example there. But now we have the question, what order do I resolve these collisions in? Because right there, I just said my collision, maybe I just add them in the order that I detect them. That's fine. I just keep a vector, just an array, which is ordered, and I just loop through them in the order that I found them. And that works perfectly 100% exactly correct in cases like this where A is not moving. But now, let's look at another case where we have a very similar wall, just made up of a bunch of boxes. I'll say these are B and C, and I have my A here. And A is, once again, intersecting both B and C, and it's also moving to the right. So if this is some kind of game, you could assume that, okay, my player is pressing both up and right, so they should be sliding, you know, just to the right along the wall, because the wall prevents them from moving up, so they should be going all the way left or all the way right. But what happens here is if I resolve them in the wrong order, I end up with some very annoying results, actually. Not annoying, again, not annoying in the sense that it's just inefficient or it's unsatisfying or anything like that, but annoying in the sense that it just does not work. The algorithm fails to do what it's supposed to do correctly, which is just prevent the player from moving through the wall and allowing them to still slide along it. So let's look at that. Let's say that in this case, I guess I should rename this, because so far I've been assuming that like these are stored in this order. So let's say I check the collision between A and B first. So I have my little collection C here of collisions, and I say, okay, I've got one between A and B. Great. Then I also have one between A and B again. No. Oh boy. Between A and C, right there. Okay, and now that's my whole processing step. I've found all the collisions. Now I go through the loop and I resolve them just in that exact order. Okay, so first check, is A still intersecting B? Yes, obviously we haven't done anything yet. Okay, resolve it. So I push A out. Oh boy, I just erased everything. Okay, that's not gonna happen. But I push A out from the wall, so it's no longer intersecting B. Okay, great. Now, in order to do that though, let's sort of drop down a level and actually consider the resolution of that intersection. So we'll only look at A and B, and their orientation is something like this. So A's velocity is, you know, up and to the right. That's the way my player is telling it to move. But the velocity we want is just that. And basically what that means is that we need to negate the upward component. We need to prevent A from moving. But what happens here is this resolution is not necessarily guaranteed to push A down. Because depending on how A is intersecting B, if I draw this in just a slightly different way, well, first I'll draw it this way. The best way to resolve an intersection can be defined as by whichever one requires the least amount of movement. So in this case, I can either move A down this amount or move A right this amount. So clearly the algorithm will choose to move A down, which is fine. That's exactly what we want. But if I had just a slightly different orientation, sort of the opposite, where now I can either move A left a tiny bit or down a big bit, then it's going to choose to move it left. Okay. So what happens in our picture here then? Well, I'll just draw a new one because I don't want to clutter everything up. So we have C and B, and now A has been moved left. And in fact, let me draw A a bit better just to make that more clear. It won't let me erase. There we go. So the shortest distance here is moving it left rather than moving it down. So what that means is A remains at its current vertical position, but it's just shifted left a bit. So it'll be intersecting C like that. Okay, so that was my collision with B, resolved. A is no longer intersecting B, but now A is intersecting C. And to resolve that, there is only one way to resolve it, which is to push it down. So my next and final step of this algorithm would look like that, which is great, right? We say, okay, so I've solved this problem because A is no longer moving upwards through the wall. But the key is in that lower level that we looked at. The way that intersections are actually resolved is by manipulating the velocity of the objects involved. And in the case of this first intersection here between A and B, what we did is we changed A's velocity so that it would no longer be moving right so much that it would intersect B. We changed it so that it would be moving right just enough to move to the edge of B and not anything more, because otherwise there would be an intersection. And the result is either, instead of this sort of big right-facing arrow representing our player's velocity, we get a smaller one or none at all. We just sort of, as we're moving completely along this flush surface, or this seemingly flush surface that is composed of multiple boxes, if they're not resolved in the correct order, we end up sort of stuttering. Like when we get to this corner here, we'll hit B, which will push us back. C will push us out. So we're not intersecting, but it messed up our velocity. Now let's look at this from the other perspective. If we resolved this in the other order, so if we resolve the collision between A and C first, and then the one between A and B. So this is our, oh man, I'll try and keep it consistent here. This is our starting orientation. So if we resolve the collision between C and B first, then our next sort of state will look like that. And what do you know? That also resolved the collision between B and C. So then this if statement up here, if A dot intersects B, that's going to return false. So we no longer do anything for B. And what that means is all C had to do is change A's Y velocity to push it down. And so A still has that right velocity that we were looking for. Okay, so what am I trying to say here? Well, yeah. So that is one way to think about it. Yeah, doing it by area of like how much of A is intersecting B, right? And I believe that's equivalent to what I'm about to say, which is the distance between A and B. We can track the, in this loop up here where we are identifying collisions, we're checking if A intersects B and then setting a collision. We can check at what time A will intersect B. And I don't have time to explain like exactly what that means. When I go through a more formal description of this problem next time, I will. But essentially each frame of a game happens over a certain period of time, a discrete amount of time. And an intersection can happen at any point within that section of time. And in this case, because A is here and C is there and B is there and A is moving to the right, A will hit C first. A clean, I believe, clear way to see this would be if I were to draw the state before we have a collision. So A is coming in from this way. And remember, my player is pressing up and to the right. So this is like, let's just call it frame 1. And then on frame 2, this would be the result if we don't resolve those collisions before they happen. So in this case, well, what's the difference or the distance between A and C? I'm not going to talk about exactly how that's computed, but just, you know, intuitively, if we sort of approximate it with midpoints, clearly A is closer to C than it is to B, and therefore C needs to be resolved before B. We're not accounting for that. No, area is not a better way to do it. So the question was, what if A is rotated basically relative to B and C? So that is something that clearly that is a solvable problem, but that's not the example I'm giving here. When the solution I'm going to show you to this problem is independent of that. It can account for those cases depending on how you implement it. Basically, I have separated the duties of tracking all of the objects, detecting collisions, resolving them in the correct order, and what it actually means to detect an intersection and resolve an intersection. Because there are two different methods for if these boxes can be rotated, if they're boxes at all, are they polygons, are they convex, are they concave? You can go crazy in depth. But this is the clearest way to, this like super simple example is the clearest way to see the actual point of resolving them in the correct order. Okay, so just to tie everything together in the final step here, we see that the distance between A and C is less than the distance between A and B, meaning that between frames 1 and frame 2, in that sort of discrete time step that this frame takes up, A will intersect C first. And so therefore, if our game is to be physically accurate, then A should be, the collision between A and C should be resolved first. And what we can do is actually keep this exact same code. All we have to do is change the type of our collision container here. So I have, that should be called collisions, I guess. In these cases, I was just sort of assuming that collisions is an array or a list, just something that we add to in the order that we see things. But if instead what we do is we make, let me scroll down, we can make collisions, oh my gosh. There. So instead of just saying, okay, I have a collision between A and B, I'll add it to my list. I have a collision between A and C, I'll add it to my list, which as we saw is not the correct order to resolve them in. We can do this using a tree of some kind. I won't go into what it is because it doesn't really matter. We can do it using a tree where the value that the tree uses to determine precedence, to determine whether one node in the tree is less than another node, is the time between the time within the current frame that collision will occur. So let's say, just to give these some concrete values, that the time between A and C is 0.1 and between B it's like 0.2 or something. They're close, but C is very clearly less than B. Now what happens in this case, if my collisions is a tree, then I will insert A and B first, which is the root. So that's 0.2. And then I will insert A and C next. And assuming I've set it up properly so that time is sorted sort of as you'd expect it to, where lower values go to the left, then what this looks like is this. And now what my for loop up here represents for each collision C, just go through it and in some sort of order, whereas where this was a vector, that just meant from left to right. But now that it's a tree, it means implicitly, it sort of means give me a pre-order traversal of this tree. Pre-order, meaning the pattern for that is L in R. Visit my left children, myself, then my right children, meaning that I will start at the bottom left corner of my tree. In this case, that is AC. And then next, I will do the root. So I resolve them in the correct order there. And you could use sort of mathematical induction, I guess, to prove that this would work for in elements inserted into this tree. But that's not particularly interesting. Okay, so hopefully I sort of gave you a better description of the things that I just sort of rushed over last time. The graphs and stuff, I don't know, there's more I wanted to talk about there, but I ran out of time. And this is what we're going to be doing from now on. This problem, we have 2 sessions left, as I said. Next time, I will actually fully show you the problem. I have better diagrams that are pre-drawn and everything, so it doesn't look like a mess. And so if you don't fully understand the problem right now, don't worry about that. I will actually cover the full problem next time. I'm expecting that next time I will be able to get through that. And then our final meeting, which will be the Thursday after Thanksgiving break, I can actually go through and show you a solution, or at least some highlights of the solution. And in particular, I'm going to try to emphasize things that we've talked about. Many things related to time efficiency, basically. I'll certainly talk about that next time. In video games, time is money. And there are many decisions I made with regards to the way things are ordered, the particular data structures I used and all of that. And even to some degree cache coherency and stuff, and accounting for the number of dynamic memory allocations and stuff. And all of that is very low level. And I told you again and again and again that even though it's low level, it's still good to know. Hopefully I will be able to prove to you that it is good to know. And I can actually show you this thing in action in a real application running, so that you can realize the benefits of those things and how they contribute to fast code or good code. Okay, I went a little over this time, but thank you for coming. And I just want to do a sanity check here and make sure that next week, yes, okay, so we are meeting next week and then not the week after that because that's Thanksgiving. But then our final meeting is December 2nd, which is also a Thursday. So just 3 weeks from now. Okay, so I'll see you next Thursday.